All right, good morning, good afternoon, everybody. We are working on lesson 5.6 today. This is going to begin with a problem that you need to do on blank paper. So, well, either printer paper or line paper, whatever you can find. So this picture was taken in a store. It looks like a Staples. And the smart TV is an 80-inch TV. And the claim at the top, the advertisement, is that it's more than double the screen area of a 55-inch class TV. Question is the store's claim true? And the note in blue here that the TV classifications are based on diagonal length. So if you see an 80-inch TV, it means from corner to opposite corner. It's the viewing area from the corner to corner. So pause the video here and make a conjecture. See if you can figure out whether the area would in fact be double the area of the smaller TV. Okay, if you have not yet attempted this and you just unpause, pause again, try it, and then come back. All right, so we should be ready to go here. So what I've done is I've drawn an 80-inch TV and a 55-inch TV, and I've got a width and a length for both. So W1, L1 for the big TV and W2, L2 for the small TV. Now the way proportions work, since these are both rectangles, we can say that the proportional ratio of these TVs is 80 to 55. So I've established that here. 80 divided by 55 is a 1.45 repeating scale factor. Or if I reduce it 16/11ths, and I'm going to use the reduced fraction here because I want it to stay as exact as I can as I'm doing these calculations. So what I can say then is that the big TV is equal to, the width is equal to 16/11ths of the width of the small TV, which is larger than the small TV if I multiply by a fraction bigger than 1. So that's correct. And then the length is also 16/11ths of the second length. So the reason why I'd want to do that is because now I want to compare the two areas to see what I'm dealing with. So if I take width times length for each TV and try to compare them, so there's the 55-inch TV, it's width 2 times length 2, and the 80-inch TV would be 16/11ths width 2 times 16/11ths length 2. Setting those equal because I've used the correct scale factor here. So now going to solve this, what I want to see is, do I have a scale factor, a final scale factor that is double? Well, on the 80-inch TV, I have a width 2 and a length 2, just like I do on the 55-inch TV. So if I take the 16/11ths times the other 16/11ths, what I get is 256 over 121. So if you divide that, that is going to come out a little bit more than 2 because 121 times 2 would be 242. So 256 is bigger than twice the 121. So that scale factor is a little more than 2, which tells me that this advertiser's claim is actually correct. Even though you're looking at the dimensions, 80 and 55, definitely not double. You may have predicted that that's false advertising. But when you do the math, no matter how long the widths and lengths were, you end up with a scale factor that's bigger than 2. So that does in fact work. All right, let's go into our work on page 1 of section 5.6, talking about Pythagorean theorem, which is something that you have worked with in the past. So I'm not going to dwell on this too much. Just go cover some basics. So a squared plus b squared equals c squared, where c must be the hypotenuse. You have to have a right angle. You follow that right angle across to the opposite side. That's your c. The legs are interchangeable. You can use either one as a and the other one as b. So if I'm just solving for a missing side, I have to identify what side I'm looking at. So a 5 and a 12, I can do 5 squared plus 12 squared equals c squared, which would mean square rooting the sum of 5 squared plus 12 squared. And that comes out to 25 plus 144, 169. Square root there is 13. The one next to it has a 12 and a 20, but the 12 and the 20 are not the legs this time, so I need to leave a b unknown. And that's something that people get tripped up on sometimes. You want to make sure that that hypotenuse ends up in the right spot. And so when I solve this one, I have to subtract the 12 squared and then square root the difference. It comes out to 16. Now I want to take this minute to show you some shortcuts to this, because if you can learn some basic Pythagorean triples, it is going to help you solve triangles much faster. So there are 4 sets of integers that work in Pythagorean theorem that come up commonly. And there are more Pythagorean triples. There are a lot of Pythagorean triples. However, these are the four that come up commonly in geometry problems. So what I mean by this is if you have three side lengths in a right triangle that are 3, 4, and 5, they will work in Pythagorean theorem. 3 squared plus 4 squared equals 5 squared. Same thing with 5, 12, and 13. 8 squared plus 15 squared equals 17 squared, and 7 squared plus 24 squared equals 25 squared. The reason why you want to know those triples is if you see any two of them, then the third one has to be there. So on this first problem, when I saw the 5 and the 12, if I know my triples, then I can get that the third side is 13 without even having to calculate it. And the same thing applies if I have a multiple of that. So if I saw a 10 and a 24 to begin with and I didn't know the third side, what I could do is take the 10 and the 24 and reduce them by 2. I'd get 5 and 12. And if the reduced versions are part of a triple, then the third part also has to be part of a triple, but it would be scaled back up by what I reduced by. So if I had a 5 and a 12 in reduced form, then I would also have a 13 in reduced form, which means the third side would have had to be 26. So you can use Pythag triples in reduced form, or you can use them in multiples form. So what this one would have been, if I took the 12 and the 20 and reduced them to 3 and 5, then I'm seeing two parts of a triple. The third part would have had to be 4, and therefore, since I reduced by 4, this has to be times 4. So triples can really help. All right, so going to the second part of page 1, we're looking for simplest radical form as well as nearest tenth. So looking at the hypotenuse in part A, I have an unlabeled side. I call that C to start with. 5 squared plus 5 squared equals C squared. So that gives me 50 because I'd have 25 plus 25. To do the simplest radical form, what you want to do is split that 50 into a product, where one of the numbers in the product is a square number. So 5 times 10 wouldn't be helpful here, but 25 times 2 is because the 25 solves. So you just write it as two separate radicals, where the product equals the original number. Solve the part that solves nicely, and leave the other part inside. To go to the nearest tenth, you would just simply type square root 50. I did not do that in advance, so I'll do that right now. Square root 50 is 7.07, so nearest tenth would be 7.1. So approximate value is 7.1. Okay, so it depends on what the directions say about how you want to write that final answer. I did the same thing over here, except that I left B unknown because I had the hypotenuse this time. So it's 8 squared minus 4 squared, which is 48. Split that into 16 times 3 and solve it. You end up with 4 root 3. And then when I do that as a decimal version, I'm ending up with 6.9. So B would be approximately 6.9. All right, moving on to page 2. So we do have right triangles in several places in context problems. And so the first is a classic problem with the ladder going up to a wall. You'll see this kind of thing a lot with geometry problems. So 12-foot long ladder would be the hypotenuse in this case because the ladder is what leans on the diagonal. And the base is 4 feet from the bottom of the wall, so that's labeled as well. If you're drawing your own, you would just draw a triangle. You don't have to get very detailed with it. You would just draw the triangle, label the parts. I've got a B for the height. You could use an A for the height, whatever you want. Just don't use a C because that'll confuse you. 12 squared gets subtracted minus 4 squared, square root, and solve it with a decimal. So you notice how this one didn't say simplest radical form, and that's because we're looking at a context problem where radicals don't help that much. So you would want a decimal version of it if you were looking for a measurement. So that's why we have that there and not the radical form on that one. All right, exercise 4, equilateral triangle has a side length of 10 inches. So go ahead and draw your equilateral triangle with side lengths, with just label side lengths 10. And it doesn't have to be a perfect equilateral triangle. I just messed up mine real quick there. All right, so I've got 10 in each location. And what we're trying to do is figure out the area of the triangle in simplest radical form. So we know the area of a triangle is 1/2 base times height, where height is a perpendicular from a vertex. So we've got to drop that down first and make that perpendicular. So in an equilateral triangle, I know this isn't drawn to scale, but in an equilateral triangle, if you drop a vertex down, you're splitting that triangle in half. And so we would have 5 and 5. And so the height is still unknown, but we can easily calculate it just by solving one side of this, the right triangle part. So I can say that 5 squared plus h squared equals 10 squared. So subtracting, I would have h squared equals, what's that going to be? 100 minus 25 is 75. So h is equal to root 75, and it wants it in simplest radical form. So let's simplify this root and say it's 25 times 3, which is 5 root 3. So going back to my area formula, my area would be 1/2 times the base, which was 10. That's this segment down here, times the height, which I just calculated to be 5 root 3. I don't want to put that in the calculator because I don't want a decimal answer for that. So I want to work around the radical. So 1/2 times 10 would be 5, times another 5 would be 25, and I write 25 root 3. That's the simplest radical form. So just pay attention to the directions so you know what style answer to give. And finally, exercise 5, working on a grid. So we've got line segment AB already plotted with the endpoints. We want to find the length of it. So in order to do the length of it, what we really are looking for is where is the triangle that this line forms. So if I draw a right triangle whose legs are horizontal and vertical, we can do that here. So I go A straight up. I'm making a dotted line here, but you could make a solid one if you want. And then I go across to B. Okay, and I just need to figure out how far that is. So that's 6 units this way. And it looks like 8 units this way. So that's easy to do. And then I want to know the hypotenuse. Well, it says to use Pythagorean theorem, but remember we can use triples, right? We talked about that at the beginning of this lesson. So if I reduce these, they both reduce by 2. That gives me a 3 and a 4. What am I missing in a triple? I'm missing a 5. And so since I reduced by 2, I can multiply by 2 and say that side is 10. So AB equals 10. And that would check out if you did the Pythagorean theorem, but use triples when you can. All right, so now that we are completed with this portion, the next thing you need to do is complete pages 3 and 4. Those answers can then be checked on Class Kick 5.6. So we should have that complete as your next task.